Hello everyone, welcome back to the channel. So today we are diving into a deep learning algorithm for the sequential data, that is the GRU. We have already covered RNN, we have already covered the LSTM. Now moving forward, we are getting started with GRU, that is the Gated Recurrent Unit. If you have already watched my video on the LSTM, then this will be feels like nice breathing part to you. Okay, so let's start with that. So what exactly is GRU? A GRU is a recurrent neural network variant that simplifies the LSTM. That how does it simplifies it? Okay, so there are two main ways. Firstly, it merges the cell state and the hidden state into just one single state vector, which we called as h of t. Remember, in LSTM we have two separate things floating around the cell state and the hidden state. GRU say nah, just let's keep it one only. Secondly, it reduces the number of gates from 3 to 2. Instead of forget gate, input gate, and output gate, you have only two gates. One is the update gate, and another one is the reset gate. Okay. Now here's the core insight to really lock your understanding. LSTM gives you final gain control with its three separate gates, but that comes with a parameter cost. More weight will cause more learning and slower training. GRU asks a smart question that can we use similar gradient preserving behavior with a fewer grades and no separate memory cell? So if the answer is yes, then the update gate will alone take it. Okay. Now why not just to use LSTM? So the great question is states. LSTM has cell states plus the hidden state. GRU has only one hidden state. Gates. LSTM has three gates. GRU has two. For the parameters, LSTM is 4 times as vanilla RNN, GRU is only 3 times. Training speed, GRU train faster because it has fewer parameter. Then for the performance, LSTM is stronger on the long sequence, GRU is comparably on more tasks but slightly weaker on a very long range. Okay, now let's see. X of t is our input at time t, and we write h of t minus 1 comma xt. To mean we just sticking to the previous hidden state. Now we have two things. One is the update gate, so that the formula is given here. Second one is the reset gate, and same for the equation is given here. Third one is the candidate hidden state. You can see that h of t equals to 10h functions, it is given. Notice something cool here, that the reset gate r of t multiplies with the h of t minus 1 before we compute the candidate. Okay, that's how we reset the gate filter from our old information. Finally, the actual hidden state is being updated like this. This is literally just a weighted blend, a linear interpolation between keeping the old state and the use of the new candidate. Simple, elegant, and powerful. And just like any other neural network, GRU trained by minimizing a sequence loss, cross entropy, or a MAC depending on the task, using backpropagation through time or BPTT. Picture you a singular GRU cell. The previous hidden state h of t minus 1 comes into the input, x of t comes in. Unlike LSTM, there is no separate cell state highway running through it. So h of t minus 1 enters the cell once and get combined with the candidate part and the update gate, decided to give a final product. Deep diving into the update gate, let's understand it better. So it controls the trade-off between the past bridge and the new bridge information. If z of t is close to 0, then h of t minus 1 stay almost unchanged, long memory. If z of t is close to 1, then h of t minus 1 get completely replaced by a new candidate. So that's how it works. Now deep diving into the reset gate. Now the reset gate, this one control how much of the previous hidden state contribute to the new state. If r of t is close to 0, the unit basically forget the previous state while building the candidate, letting it dropping irrelevant past context to the backside. Now we have something called as gradient flow, that while GRU handles long sequence. Okay, so this is equation given here. If you see that the 1 minus z of t term is the magical part, where z of t is small, this create a linear gate control path for the gradient to flow back through time. This is very similar in spirit to the LSTM forget gate mechanism, and it actually happens to prevent vanishing gradient. Moving forward towards the parameter count. Okay, so that's a maths here. For input size d and the hidden states h, each of the three components, update gate, reset gate, and the candidate has its own weight matrix. Parameters equals to 3 times d plus h times h plus h. Example, say d equals to 100 and h equals to 128. Now 3 times of this equals to somewhere around on calculating 87,936 parameters. To put that all in perspective, there is a 3 time a vanilla RNN parameter count, but only about 75% of what an equivalent LSTM would need. Now moving forward towards the design parameters. Hidden state H control memory capacity typically 64 to 1024. Sequential length, your context window beyond a point, your truncated BPTT usually has 10 to 500 plus steps. Number of layers is also an important part of this, typically 1 to 4. Then the gradient clipping, which we have already discussed, usually between 1 to 5. Then dropout and the upgate gate bias in it. Some of the training and the regularization techniques are also being given. For example, the gradient clipping that we have already discussed, the truncated BPTT, only the back propagation k steps at a time, keeping training trackable on the long sequence. Then we have recurrent dropout. The same dropout masking is being reused across the time step instead of resampling each time. Then we have the layer normalization, stabilizes the gate activation across time. Then we have the update gate bias in it that set z of t to start from a small to the model favor, retaining the h of t minus 1 early on. Then we have early stop also. Keep an eye on the validation loss and stop before you overfit to the sequence. There are some of the type of the variant for this, like the vanilla GRU, minimal GRU, bidirectional GRU, stack GRU, encoder and decoder GRU. Everything is written about that. You can read it. Actually, it's not so important. That's why I'm not going into depth. Then we have some of the real world application for it, like the language modeling, machine translation, speech recognition, time series forecasting, segment analysis, mobile edge deployment, and the anomaly detection. Okay, moving forward towards some of the key takeaway that are GRU merges the LSTM cell state and the hidden state into one single vector h of t. The upgrade gate z of t along balance the retaining h of t minus 1 versus writing the new candidate information. The reset gate control how much the past state feed into the new candidate, great for resetting the constant at the boundaries. Then we have GRU that have 3x parameter than the vanilla RNN and compared to 4x for the LSTM. Fewer parameters means faster training. The 1 minus z of t term that we have already discussed gives a gradient preserving path similar in spirit to the LSTM forget gate. Now, GRU often matches the LSTM performance on small to medium dataset, through LSTM can edge ahead on very long range dependency. Bidirectional and stack variant extend GRU for rich context and hierarchical feature learning. So the bottom line is that GRU is a strong default choice when you are limiting on computer memory and the training dataset as compared to LSTM. Wrapping up, we have covered everything about the GRU. We have seen the comparison between the GRU and LSTM and how it is better than the vanilla RNN and the LSTM. Okay, we have also discussed some of the parameters that are being important for this. So, thank you.